studying mineral microscopy, we think of light in terms of its wave nature, in spite of what you may have heard in your physics class about the dual properties of light. For optical purposes, it's the wave nature of light that we emphasize. Now, this is a simple diagram of wave, and I have put on this diagram, or indicated, really two key directions of the wave. And one direction is the direction measured across in the diagram like this, which represents the direction in which the light ray, which is a coherent mass of light, is moving. And this movement, or propagation of the light, corresponds to the wave here, which has crests and troughs in this kind of position, which with time migrates to a second position. And so that the movement, it's the movement of a particular crest or trough of the wave in this particular direction that corresponds to the propagation of the wave. This is the propagation direction of the wave. But if we took a single reference point along this wave, there is another direction that we can define, and that is the vibration direction, or the way in which the wave is vibrating. And if you look again at this diagram, you can see that as far as this particular point is concerned, the wave, as it propagates, actually vibrates up and down with respect to this point, so that this direction then represents a vibration direction. And every wave, or every ray of light, then we can speak of as having a propagation direction and a vibration direction. Now, some more definitions that I want to indicate as far as waves are concerned, waves of light, are shown in this diagram, where again we indicate the propagation direction in this way, the vibration direction in this way. And I've labeled here a crest of the wave with a C, symbol C, and T for trough of the wave. These are reference positions on the wave, and they can be located for any coherent mass of ray. You can produce something called a wave front, which might correspond to some particular trough or a crest from a coherent light source. And this gives you an idea of the pattern of light propagation from a individual source. We'll be using then wave front positions, which typically would correspond, let's say, to a crest or a trough, some particular reference crest or trough of the wave at some point in time. There's also a wavelength, and a wavelength is measured from, typically from one crest to the next crest, or from one trough to the next trough. And this wavelength is different, of course, for different light rays. There's also a property called the amplitude, which can be measured here. It's really the half height of the light ray, and the amplitude is proportional to the intensity of the light ray. And so the more intense the light ray, then the higher this amplitude is. So these are then the basic definitions of propagation direction, the vibration direction, crest, trough, wavelength, amplitude. Now, let's look at the relationship then of wavelength throughout the electromagnetic spectrum, because there really are a whole spectrum of waves that we deal with, and as far as optical mineralogy is concerned, we're restricted to only a very small portion of this electromagnetic spectrum. And so what I've shown here is wavelength across the top here in a unit called nanometers. Nanometer is 1 × 10⁻⁹ meters. And so I'm going here over many orders of magnitude, extending from electromagnetic waves called gamma rays, through X-rays, through ultraviolet, and this narrow orange band here corresponds to the visible spectrum, to infrared, to shortwave radio, to radio waves, and finally to long wave. Going from 10⁻³ nanometers to over 10⁻⁻⁻ nanometers. The visible spectrum is just this very narrow band of of wavelengths, and those are the ones that really concern us. Now, we can also express this in terms of the frequency of the wave, and that is how often there is an oscillation from of a particular vibration direction within the wave. So the frequency is measured in the number of cycles per second, and there also is a systematic relationship across the spectrum with very, very high frequencies, 10 to the 20th cycles per second here in the gamma and X-ray region, on down to 10 to the 7th cycles per second within the long wave radio range. The visible spectrum then is between 10 to the 14th and 10 to the 15th cycles per second. Now the relationship then between frequency and wavelength is shown by a simple equation, which I have here, which relates the velocity of light in a vacuum to frequency and wavelength. And again here, if we specify the units of wavelength in nanometers, or 10 to the minus 9 meters, frequency in terms of cycles per second, and then the velocity of light in a vacuum in the same units is 3 times 10 to the 17th nanometers per second. So this shows then the really inverse relationship then between frequency and wavelength, as long as we're talking about materials in a vacuum. Well, let's look at the visible spectrum then, this very small section of the total electromagnetic spectrum that's relative to our mineral microscopy experiments. So this is just shown schematically, and again I have a wavelength across the top from short waves here, or about the edge of the visible spectrum for most people occurs around 400 nanometers. This is violet color. And the other edge of the visible spectrum is marked by red light in approximately 650 nanometers. And in between then we go through blue, green, yellow, orange, red. And of course the frequency increases in this direction. Here's ultraviolet, located here, infrared, located here. Again, these both invisible. And so we're talking about in terms of the light spectrum that we use is white light. And white light is a combination of all these wavelengths that is operating through the petrographic microscope. And the blue filter, of course, is designed to balance this spectrum so that we have all wavelengths represented more or less equally, and we get a balanced color of light. Now, light travels different speeds in different substances. Here's a modern evaluation then of the velocity of light in a vacuum. It's approximately 3 times 10 to the 8th meters per second. This shows the level of uncertainty as of a few years ago, and I suppose this improves all the time with different techniques of measurement. We don't need to worry about this in detail. What we need to recognize, though, is that in any substance, for example, a crystal, a transparent crystal, the velocity of light is less than the velocity of light in a vacuum. And so because of this, then we need to define a parameter that helps us measure the speed of light in other kinds of transparent substances. And so this definition then corresponds to something we call the index of refraction. The index of refraction, for this we use the symbol n. So the index of refraction for substance X then is n sub n. And it's defined very simply as the velocity of light in a vacuum divided by the velocity of light in substance X. Okay, so the index of refraction then is a parameter which is something greater than 1. There is no substance in which light travels more rapidly than it does in a vacuum. So the index of refraction is some parameter greater than 1. Now the control of the index of refraction is depends partly on the density of the substance. It depends on other parameters too, but density is the simplest single parameter to think about that has a strong influence on the index of refraction. For example, if you look at air, the index of refraction of air is almost exactly 1. And air is not very dense. It does very little in terms of slowing the velocity of light, and so the velocity of light in air is nearly identical with its velocity in a vacuum. But when we talk about crystals, typical kinds of transparent crystals that we're going to be working with the petrographic microscope, light is slowed down very dramatically, such a way that the index of refraction generally varies between about 1.3 and 3.3 for typical kinds of crystals. In fact, most crystals occupy an even narrower range between about 1.4 and 1.8, and it's only a rare crystal that slows light by a factor of 3. Another thing about the index of refraction is that it depends on wavelength. It's wavelength dependent. And we can show this, for example, with air. The index of refraction of air is actually different for violet light than it is for red light. And here you show a very, very slight difference. And this is true of any substance. Air is no exception. It seems that the shorter wavelength violet rays are slowed more than the longer wavelength red rays. And that means that for any substance, the index of refraction is slightly lower for red light than it is for violet light. And this means that if you're really going to rigorously define the index of refraction, you have to specify what wavelength you are referring to. Now, by convention, for the visible spectrum and for mineral microscopy, when we're using white light, we're talking about the index of refraction measured in terms of yellow light. Yellow is the middle of the visible spectrum, and this is the wavelength which is of main interest. So when we talk about index of refraction, if we make no stipulation about wavelength, we mean the wavelength for yellow light, or approximately 550 nanometers, the middle of the visible spectrum. So part of refraction, then, one part that we need to worry about is the fact that light is slowed. But another aspect of refraction is that is at the interface, light can be bent. And I can show the bending of light by using this simple diagram and by using a lens. You can see that if I impose this lens on this diagram, I can actually bend the position of the intersection of the cross artificially, so that the light passing through this lens is not only slowed down because the glass is denser, but it also can be bent depending on the angular relationship that I have between the surface of the diagram and the lens itself. So part of refraction then is actual bending of light which occurs. Another thing that I can show is really the separation of these wavelengths that occurs associated with refraction. And I'll do this by using a prism. This is the prism. It's really a triangular piece. This is actually a piece of plastic. But the prism has an obvious triangular relationship between the surfaces, and some of these are transparent. Now, if I take this prism and we're going to look at a completely black line on a white background, I think I can show you that in the course of refraction of this line, I can actually separate the colors of the spectrum. And if you look at this line now, you can see that one side of the black line appears blue, the other side appears red. This is the separation, actually, of the visible spectrum due to the fact that the bending of light is wavelength dependent. Not only do we bend light when we refract it, but we bend certain wavelengths of light more than other wavelengths of light. So we slow them differentially, we bend them differentially when refraction occurs. So this is really an artificial generation of color that you can do with a prism that results from the fact that some wavelengths of light are bent more. Diagrammatically, I can show this here by looking at the prism and the the way wavelengths of light have different angular relationships. Here, the white light coming into this prism, the blue or the violet light being bent considerably more than the red light at the angular relationship. So there's a slowing, differential slowing of wavelengths, and also a difference in the bending of the light as a function of wavelength. So refraction results in slowing and also bending of light. Now we can graphically show refraction in this kind of way, where we're talking about a simple interface. Now, this horizontal line then represents the boundary between one substance over here, which has a high index of refraction, and another substance over here, which has a low index of refraction. You could think of this interface then as let's say, the boundary between a crystal up here at the top and air, for example, at the bottom. The crystal has a higher index of refraction, so light travels more slowly within it. The air has a lower index of refraction, so light travels faster. Now, so refraction can be defined in terms of a couple of angles, and these angles are actually measured from the perpendicular to the interface surface, which is shown here by the pencil. And there's an angle of incidence here, which is measured here. This is the propagation direction of the light traveling this way. And you can see that the light is actually bent, that this angle measured from the perpendicular is not the same as this angle. This is the angle of incidence, I. This is the angle of refraction, R. Okay, so R in this particular case is larger than I. And this is the normal relationship that would occur if you're going from a substance of higher index of refraction into lower. If you're going the other direction, the angular relationships are the same. If you go from a lower index material to a higher index material, then the light will be bent exactly in the reverse of this. One way of saying this is that going into a substance of lower index of refraction, light is bent away from the perpendicular in this kind of form. Going into a substance of higher index of refraction, light is bent toward the perpendicular. Now there's a strict mathematical relationship between the angle of incidence and the angle of refraction, which is called Snell's law, taken right out of your introductory physics book, in which we can talk about these two indexes of refraction of substance 2 and substance 1, and the ratio of these two indices of refraction is the ratio of the sine of the angle of incidence over the sine of the angle of refraction. This is Snell's law, and this is the rigorous statement of the bending of light as part of refraction. When light is coming from a light source, typically the light rays are propagating in a single direction. The light can be focused, but the vibration directions may be relatively random, and typically are random. There may be light vibrating in this direction as it comes toward you. There may be light vibrating in a vertical direction. There may be some vibrating in the horizontal direction. And we need to regulate this in order to take advantage of the optical microscope. And in order to do this, then we use something called a polarizing screen. Polarizing screen looks like this, and you can see some decrease in intensity of the light that has occurred. And this happens because the only light that's permitted through this polarizer is light that is vibrating in a particular vibration direction. In this case, I have the polarizing screen oriented north-south. I have a little string across this that shows the permissible vibration direction in this particular polarizing screen. And so there's one of these polarizing screens in the polarizer below the stage of the microscope. And there's another one that's located above the microscope stage. And if we position these polarizers properly for the petrographic microscope, which I'm doing now, get the vibration directions exactly at 90 degrees to each other, then no light is transmitted. You can see this looks completely black. And that's the way the microscope is with cross polars. It has exactly opposed polarizers, and so no light is transmitted if you're not looking at any particular specimen. Now you might ask, why in the world do we want to look at anything when there's no light transmitted? And of course the answer is that if you have crystals in between, sometimes you do get propagation of light because of what the crystals do to the light as it passes through them. In order to demonstrate this, I'm going to use a overhead projector setup here, and I've placed these two polarizers on the overhead projector here, and I put them in such a way that the lower polarizer, the vibration direction of the lower polarizer is east-west, just like it is in your microscope, and the upper polarizer is north-south. That's indicated by the other string here. And the light is on so that we're getting actually propagation of light through this. I can show this to you by the minute I begin to uncross the polarizers. You can begin to see the light coming. And if I cross them, then you can see the intensity of light decreases. Now let's see what happens if we put certain kinds of crystals between these polarizing screens. And I have various types of crystals here that I'm going to use. And so I'm going to put a calcite crystal here on the screen. I'm going to put a fluorite crystal here, which are really two types of crystals that we see commonly. Now, these crystals show up very clearly. They have certain boundary refractions that occur, so you can see the edges. That's because of refraction that occurs with these angular boundaries. But you can also see here with the upper polarizing screen removed, that light passes right through these. They are transparent. And most minerals, if you cut them thin enough, these are not particularly thin, they're measured in centimeters of thickness, and they're still, of course, transparent. Other minerals have to be cut thinner, but nearly all silicates are transparent to light, and light propagates directly through them. And if I use the upper polarizer here, you can see that as I cross the polars in this sort of form, I can actually still see the outlines of the crystals. This is because of the boundary conditions. But I think I can demonstrate to you that these two crystals actually behave quite differently between cross polars. Let's look at the calcite first. So I'll just set the fluoride aside for a minute, and we'll look at the calcite crystal grain. And I'm going to just actually reach in here in between the polarizers and move this calcite grain around. And as I rotate this grain, I think you can see that at some positions it is not well illuminated, but at other positions it transmits a great deal of light. This is characteristic of one kind of crystal which we call anisotropic. In anisotropic crystals, between cross polarizers, they transmit light, especially at certain positions of rotation. So if you're thinking about this in terms of a thin section on your stage, you'd have this crystal in some kind of mount in a thin section, or perhaps in an immersion mount lying on your stage, and as you rotate the stage, there would be positions in which it is dark and other positions in which it's very nicely illuminated, as it is here. This kind of position here where the anisotropic crystal is dark is called extinction. And extinction occurs 4 times during the rotation of any anisotropic crystal. There's another extinction position located there. We'll go down again 90 degrees again, and there's extinction again in the calcite grain. Now, so calcite has various positions when it's illuminated and various positions when it is unilluminated, an anisotropic crystal. Let's look now at the fluorite. Here's the fluorite mineral grain, and if we rotate the fluorite, we see nothing, no position in which the fluorite actually transmits light between the crossed polarizers. Fluorite is an isotropic mineral, and so an optical test between minerals that we call isotropic and those which we call anisotropic is simply to put them between cross polarizers and see if there are some rotation positions in which they transmit light. Most minerals are actually anisotropic. It's only isometric minerals like fluorite and halite which are isotropic. So most minerals are anisotropic, and they actually transmit light between cross polarizers. Well, let's look at what this optical test looks like in the microscope itself. I'm going to bring the microscope in here, and I'm going to put on the microscope stage a slide which is prepared with some isotropic and anisotropic minerals. So first, we're going to look at these mineral grains of a isotropic mineral, and I'll look at them first with the plane polarized light. And so now I can resolve these individual crystals, and you can see they have very nice crystal form that shows here, and I'll just move the plane of focus a little bit to show their outlines clearly. And now across the polarizer in the microscope, and we'll look at them in cross polarizers, and you can see that they are effectively invisible. In fact, the field of view is largely dark. I'll uncross the polar so you can see their form again, cross them again so you can observe the effect of the polarizer. Isotropic crystals seen in cross polarized light. And even though I rotate the stage, illumination of these grains never occurs. Again, I'll uncross and rotate, cross and rotate. Isotropic crystals in the test for isotropic crystals. Now I'm going to look at another mount which has anisotropic crystals on it. And we'll look at these again in the preparation mount, and again in plane polarized light. Take a look at the specimen here and rotate the grains. They look very, very similar to the isotropic mineral grain in plane polarized light, but when we cross the polars, you can see that they have illumination at most angles of rotation and go to extinction every 90 degrees. That is, each individual grain, randomly oriented, goes to extinction at every 90 degrees. So this is the response of an anisotropic crystal, and the test is really to look at the specimen with cross-polarized light. Well, we have to think about what happens to light within anisotropic crystals. Why does this optical test work? In order to demonstrate this, I have a simple little demonstration here, a few letters written on a piece of paper below here, and I have a calcite crystal, which is a typical kind of anisotropic crystal. If I put the calcite crystal in the path of these letters, I think you can see that the effect is to produce a double image of this word which I've written. Again, I'll just move the crystal in and out of the field of view. There is in fact a double image of this word. If I rotate the crystal, you can see that actually the double image changes, and one of the images moves substantially. The other one remains less influenced by the rotation. This is a phenomenon called double refraction. And all anisotropic crystals show double refraction. As it happens, calcite shows double refraction in a very dramatic way, so that you can see its effects without using a microscope at all. It's a nice transparent crystal. It shows double refraction very, very clearly. So we can look diagrammatically at what happens to light in an anisotropic crystal. And I have a simple diagram here, again showing the interface between two substances. Substance 1 up here is isotropic, substance 2 is anisotropic. And as the light ray comes to this interface, because there's a difference in the index of refraction of substance 1 and 2, of course there's bending of light and slowing of light, or speeding up of light, depending on the difference of these two. But the other difference that shows up here is that since this substance is anisotropic, there is in fact a separation of this ray into two distinct light rays. And these light rays have different angles of refraction, R2 and R1. They also are traveling at different speeds within that crystal. So that an anisotropic crystal in any particular position does not have just one index of refraction, but it has two indices of refraction of components that are traveling at different speeds. And so it's because of this double refraction that you see the double image. Now we'll have more to say about the quantification of anisotropic crystals later. I'd now like to concentrate on a very simple kind of optical test that we use very commonly. And this relates to a property which we call relief. Relief is the difference of the refractive indices between the medium and a particular crystal, or the crystal and whatever material is surrounding it. And it's defined in terms of an absolute value. So this is relief equal to the absolute value of the difference between the index of refraction of the medium and the index of refraction of the crystal. Now, in practice, we recognize relief in a qualitative way, and we get used to the definition of relief in terms of the boundary effects surrounding a crystal. For example, if we look again at this calcite crystal that we're looking at, it has a distinct relief from its surroundings because the boundary conditions are very well shown up very well. This is because there's a big difference between the index of refraction of the calcite and the air that is surrounding it. So that this calcite crystal, as we're looking at it now, stands out in very high relief. The boundary effects are very strong. We have no problem distinguishing the calcite from the air surrounding it. Now, what I want to do then is to show you some minerals in thin section that have different degrees of relief so that you can begin to relate and recognize variations within relief. And so go back to the microscope here, and I'll take a thin section mount. This thin section mount has three different minerals mounted on it, and these minerals are mounted to demonstrate differences in relief. So first I'm going to look at a mineral grain which shows what we call high relief. So I'm looking at the mineral grain now in plain polarized light. This is the way to observe relief, and I just want you to notice, I'll rotate the stage a little bit, but I want you to notice that the edges of these mineral grains are very well defined. It's very easy to discern the mineral grain itself. In fact, the edges show very, very strong refractory effects around the margins. You can see darkened edges on these particular kinds of mineral grains. This is characteristic of what we call high relief. High relief has very sharp border and corresponds to a difference in the absolute value of index of refraction of greater than 0.15. So high relief is a characteristic parameter and something you can learn to recognize within the microscope. When you see these strong boundary effects around the edges of grains, you know that there is a large difference, greater than 0.15, between the index of refraction of the mounting medium and the index of refraction of a particular mineral. Well, let's move now to a different mineral grain, and this will give us an example of moderate relief. Moderate relief is, again, we look at the mineral grain here, and you can see that the boundary effects, you can still discern the grains very easily, but the boundary effects are substantially less. And moderate relief corresponds to a difference between the index of refraction of the liquid and the crystal of between about 0.05 and 0.15. Now these variations in relief are estimated on a semi-quantitative or qualitative basis. And you just learn to recognize the difference between moderate and high relief. Let's look at a specimen now of a mineral grain in the same amount which exhibits low relief. Here are these mineral grains, again looking in plane polarized light. And I'll just point out the edges here with a pointer arrow so to show you where the edges of these grains are, because they're very, very hard to see. These mineral grains are beginning to blend into the medium, and this is because the refractory effects, or the changes in speed and the bending of light that happens at the edge of the mineral grains, is very, very slight. So these mineral grains show low relief, and the difference in the index of refraction is less than about 0.05. So again, what we've talked about in terms of simple optical tests today are twofold. One is how to recognize the difference between an anisotropic and isotropic crystal. And this you do by observing the crystal between cross polarizers and rotating the stage and watching for illumination of that mineral grain. And the second thing is the distinction between different kinds of relief and the recognition of low, moderate, and high relief as seen in a particular mineral grain in a prepared mount.